Welcome everyone to our final chapter. This is where we combine everything into one complete Capstone system. Before file-by-file walkthrough, we align on the architecture through these slides so the code is easier to understand. What are we building? We are building a production-ready AgentDesk AI support system, not a prompt demo, not a simple chatbot. This system receives customer input, retrieves grounded context with RAG, executes capabilities through MCP, applies guardrails, and then either resolves safely or escalates with persistent case tracking. Now, slide 1 in one clear narrative. The core vision is a coordinated agent workflow with 5 stages. Understand the message, retrieve context using RAG, execute tools through MCP, apply guardrails, escalate or resolve. Each stage has a clear responsibility. Understand means classifying user intent and risk context early. Retrieve means grounding responses in business knowledge, not only model memory. Execute means using MCP protocol to discover and call tools through structured contracts. Guardrails means policy has runtime authority over response safety. Escalate or resolve means risky cases become actionable tickets while safe cases are handled autonomously. Why this is not a chatbot? It uses enterprise knowledge. It runs tool-backed decisions. It enforces policy boundaries. It preserves operational continuity through lifecycle states, real-time business value, faster first response and triage, more consistent handling quality, earlier legal and security risk capture, traceable evidence for audits and quality review, reusable blueprint. The same architecture can be adapted to healthcare support, fintech operations, e-commerce care, HR service desk, and internal IT help desk workflows by changing knowledge, tools, and policy rules. Now slide 2, the architecture diagram. User and UI collect the request through Flask and Bootstrap. Run_agent orchestrates the runtime sequence. MCP client calls protocol tools. MCP server exposes tool endpoints. Tools execute business logic. RAG engine grounds responses using company_knowledge_base.json. Guardrails evaluate risk and policy. Schema contracts enforce structured outputs through agent response and trace bundle. Escalation outcomes move into ticketing engine actions. Tickets.json persists lifecycle continuity. UI insights show guardrail decision, trace payload, and case table. This full chain is the Capstone identity. Reasoning plus grounding plus capability plus safety plus operations. Session outcomes for this chapter. By the end, you should be able to explain what we built, narrate the end-to-end runtime flow, justify escalation decisions, interpret trace evidence, and map this blueprint to other business domains. With this architecture context in place, we now begin the project walkthrough. At the top level, this Capstone has a clean separation of concerns. App.py handles delivery and web orchestration entry. Templates handles user interface rendering. Data holds the knowledge base and persistent ticket history. Scripts provides repeatable verification and demo execution. Output stores generated evaluation evidence. AgentDesk_AI contains the core intelligence and workflow modules. This top-level separation already teaches an important architecture principle. In production agent systems, we do not mix interface, reasoning, policy, and operations in one place. We separate these concerns so each layer stays testable, replaceable, and understandable. Now we move into app.py, the first runtime touchpoint. App.py initializes Flask and registers root handlers. That sounds basic, but architecturally it is critical. This file is the contract boundary between user traffic and system intelligence. Everything upstream is request and response transport. Everything downstream is AI workflow and operations logic. The first function is index. Index serves get/. Its role is state hydration for the landing view. It retrieves recent tickets, prepares configuration defaults such as remote MCP URL, and renders index.html. Why this matters is subtle but important. A support console without recent case context forces operators to work blind. Index prevents that by ensuring the UI is context-aware from the first screen load. Index is not just route handling, operational situational awareness. Second function is chat. Chat handles post/chat from form submissions. This is the primary user-to-agent bridge. It reads customer_message and remote_URL, validates message presence, and passes input to run_agent. After runAgent returns, chat evaluates should escalate. If escalation is true, it creates a handoff ticket immediately using create_handoff_case. Then it renders the page with response content, trace data, selected ticket, expected workflow path, and refreshed ticket list. The deep idea here is that chat does more than present model output. It enforces workflow continuity. If the AI response indicates human intervention is required, the system does not stop at warning text. It materializes an operational artifact, the ticket, in the same transaction path. That is the difference between a conversational assistant and an enterprise support system. The third function is API_chat. API_chat is the JSON native twin of chat. It validates customer_message in request payload, runs the same orchestration pattern, triggers escalation ticket creation if needed, and returns structured JSON. Why this mirror path exists is a design maturity point. A robust Capstone should not trap intelligence behind one UI channel. It should expose the same deterministic behavior to browser clients, automation harnesses, and external integrations. API_chat gives that portability. The fourth function is ticket_action. Ticket_action handles lifecycle progression for existing cases. It receives ticket_ID, action, optional note, and duplicate linkage metadata. Then it calls apply ticket action and re-renders updated state. This route is where operational accountability happens. The AI can recommend next action, but actual case progression is persisted through explicit ticket transitions. Now let us look at the templates layer in the runtime flow. Templates/index.html is the primary operational interface where the full interaction is visible in one place. User input, agent response, trace details, escalation status, and ticket actions. This view makes it easy to follow how a single message moves from request to decision to operational outcome. Templates/index-demo-view.html is a simplified presentation variant that keeps the same core behavior while reducing visual noise, making the end-to-end flow easier to narrate clearly. Now we move to core logic in AgentDesk_AI. First file is config.py. Config.py defines settings. Settings centralizes environment-based parameters, app identity, model selection, embedding model, API key, MCP endpoint, and knowledge base path. Why this matters is not style. It is operational stability. When configuration is scattered, environments drift, defects become non-reproducible, and deployments fail unpredictably. By creating one module-level settings object and importing it across modules, the system guarantees configuration consistency. Consistency is the foundation of repeatable behavior. Second file is schema.py. Schema.py defines typed system contracts through pydantic models. Guardrail decision has should_escalate and reason. This model forces policy evaluation to be explicit. No ambiguous maybe states. Either escalation is required or it is not, and the reason must be present. Agent response includes reply, should_escalate, escalation_reason, lead_score, confidence, tools_used, and suggested_next_action. This is the primary orchestration output contract. The significance is that downstream layers no longer parse informal text. They consume a structured payload with stable semantics. That reduces integration fragility and improves observability. Trace bundle includes trace_ID, rag_context, tool_payload, and guardrail_decision. This model is the explainability backbone. If someone asks why the system responded this way, trace bundle contains the evidence chain: what was retrieved, what tools returned, and how policy decided. Without this bundle, debugging becomes guesswork. With it, debugging becomes evidence-driven. Third file is rag.py. Rag.py is the grounding engine. It prevents the model from floating on generic priors by anchoring response generation in domain-specific context. At a deeper level, RAG means retrieval augmented generation. Retrieval means we first fetch relevant knowledge from trusted business data. Augmented means that retrieved context is injected into the model decision path. Generation means the final reply is produced using that grounded context instead of only model memory. So, RAG is not a decorative add-on. It is a reliability architecture. It reduces hallucination risk, improves factual alignment, and makes answers traceable to known internal knowledge. In enterprise environments, this is essential because policy, product rules, and support procedures change over time. A model-only answer can be fluent but stale. A RAG-backed answer can be fluent and current against your own corpus. Load_knowledge_base reads knowledge entries from JSON. At first glance, this is simple I/O. In practice, this function controls corpus availability, schema assumptions, and data access resilience. If this layer is brittle, retrieval fails before ranking even starts. _embed_texts converts text into embedding vectors. This is where language becomes geometry. Semantic proximity becomes measurable in vector space. Cosine similarity computes angular closeness between vectors. This function is the ranking primitive. A stronger score means stronger semantic match. _load_kb_vectors pairs each knowledge document with its vector representation. This pre-processing step standardizes retrieval inputs and reduces runtime overhead. Simple_rag_search is the user-facing retrieval pipeline. It embeds the query, compares against stored vectors, ranks candidates, and returns top K contexts. This function strongly influences answer relevance and trust. If responses sound plausible but not specific, this is often where the weakness starts. Fourth file is tools.py. Tools.py wraps business capabilities into orchestrator-friendly functions. Search_knowledge_base calls simple_rag_search and normalizes output shape. This function is the bridge between retrieval internals and orchestration payload contracts. Score_lead applies heuristic scoring to user message signals. It estimates lead quality and returns rationale details. This enables business-aware prioritization, especially when support and sales signals overlap. Decide_escalation evaluates sensitivity and contextual risk to produce should_escalate plus reason. This function is one of the most important decision boundaries in the system. It governs the transition from autonomous handling to human handoff. If this boundary is too strict, automation value drops. If too permissive, safety and trust degrade. Fifth file is guardrails.py. Guardrails.py contains evaluate_guardrails. This function receives customer_message and tool-level escalation hints. It detects risk markers such as legal or security language, merges those signals with tool outcomes, and returns guardrail decision. Conceptually, this is policy as code. It is where organizational risk tolerance becomes executable logic. A strong guardrail layer does not just block unsafe replies. It actively routes risky cases into controlled human workflows. That is mature agent design. Sixth file is mcp_client.py. mcp_client.py is the remote capability bridge. It allows the orchestrator to consume tools through protocol calls rather than hard-coded local function invocation. At a deeper level, MCP means Model Context Protocol. It is a standardized way for an AI application to discover and call tools. Instead of tightly coupling the agent to one local Python function map, MCP introduces a protocol boundary. The agent asks the server what tools are available, then calls those tools through a structured interface. This gives portability because the same agent can work with local tools, remote tools, or hosted tool services with minimal orchestration changes. It also improves maintainability because tool providers and agent orchestration can evolve independently as long as protocol contracts remain stable. For production systems, this decoupling is a major engineering advantage. Extract text standardizes plain text extraction from tool responses with varying envelopes. Extract JSON parses JSON payloads and degrades safely on parsing failure. The key point is graceful failure. In distributed tool ecosystems, payload variability is normal. A brittle parser can crash the whole pipeline. A resilient parser protects continuity. Capstone. Tools is the central MCP orchestration function. It connects to configured MCP URL, calls retrieval, lead scoring, and escalation check tools, and aggregates outputs into a unified payload. This function decouples orchestrator intelligence from specific tool implementations. That decoupling improves extensibility and deployment flexibility. Seventh file is mcp_server.py. mcp_server.py exposes local capabilities as MCP-compatible tools. RAG_search wraps local search_knowledge_base. Lead_score wraps local score_lead. Escalation_check wraps local decide_escalation. This module demonstrates a powerful architectural pattern. Local business logic can be protocol published and remotely consumed without rewriting core algorithms. That makes capability surfaces portable across local and remote runtime topologies. In practical terms, mcp_server.py is the capability publisher and mcp_client.py is the capability consumer. Together, they create a clean contract-driven tool layer between reasoning and execution. Eighth file is ticketing.py. Ticketing.py is the human handoff lifecycle engine and persistence layer. This file transforms escalation intent into auditable operations. _now_ISO returns consistent ISO timestamps. Consistent time formatting is essential for reliable event sequencing and audits. _ensure_store guarantees ticket store existence before read or write. This prevents first run and missing file failure modes. _load_store loads persisted ticket state into memory. _save_store writes updated state back to disk. Together, these functions create durable lifecycle continuity. _event constructs standardized lifecycle event objects containing step, note, actor, and timestamp. This event normalization gives historical clarity and operational traceability. _next_ticket_ID generates sequential ticket identifiers. Deterministic ID strategy simplifies case lookup and monitoring. _normalize_message standardizes customer text for duplicate detection. Without normalization, duplicate matching fails on superficial formatting differences. List_tickets returns recent cases with limit controls. This supports efficient UI rendering while keeping operational visibility. getTicket retrieves one case by identifier. _find_duplicate_open_case scans unresolved cases for semantic duplicates. Preventing duplicate open cases avoids wasted human effort and fragmented resolution. Create_handoff. _case creates escalation tickets with duplicate prevention, initial lifecycle event creation, trace linkage, and captured agent context. This function is where AI decision becomes a countable operational work item. Apply ticket action updates lifecycle state based on explicit actions such as assign, human action completed, customer notified, close case, or mark duplicate. This is the state transition engine that drives cases from creation to closure. It is the difference between notifying and resolving. Ninth file is agent.py. Agent.py is the orchestration heart. Underscore fallback. Underscore response produces deterministic agent response when LLM generation fails. This protects service continuity. Even under model outage or generation failure, the system returns structured output with critical escalation and lead context intact. That is resilience by design. Underscore generate underscore LLM underscore response composes model context from retrieved knowledge, tool payloads, and guardrail hints, then requests a structured response. Its job is not only language generation. Its job is policy-aligned, context-grounded, action-oriented communication. Run underscore agent is the full runtime controller. Its sequence defines the Capstone contract. It creates trace underscore ID. It gathers tool intelligence through call underscore capstone underscore tools. It extracts lead and escalation signals. Runs evaluate underscore guardrails. It generates final response with underscore generate underscore LLM underscore response and fails over to underscore fallback underscore response when needed. It packages trace bundle. It returns agent response and trace bundle to caller. If run underscore agent is understood deeply, the architecture is understood completely. Because this function connects reasoning, retrieval, capability execution, policy control, and observability in one deterministic workflow. Now scripts test underscore remote underscore mcp.py validates external capability connectivity by running a sample message through the main pipeline and printing response plus trace. This verifies protocol path health in remote mode. Scripts test underscore local underscore mcp.py validates local protocol path behavior. This isolates server-side capability exposure before remote dependency variables are introduced. Scripts run underscore demo underscore cases.py executes predefined scenarios, captures outputs and traces, and writes a structured report to outputs. This script is especially important because production confidence should come from repeatable evidence, not one manual happy path demo. Data and outputs. Data company underscore knowledge underscore base dot JSON is the grounding source. Its quality, completeness, and relevance directly influence answer precision. Weak corpus quality creates weak retrieval no matter how strong the model is. Datatickets.json is persistent lifecycle storage. This file preserves operational continuity across sessions and enables audit trails for escalated cases. Outputs demo underscore report timestamp JSON files are verification artifacts. They turn scenario runs into analyzable evidence. readme.md provides setup and run paths. Deployment underscore free underscore guide.md provides deployment guidance. Now the UI displays response, trace evidence, and ticket state. Further operator actions flow through ticket underscore action and apply underscore ticket underscore action until case closure. All of this persists in tickets.json. This is the full Capstone loop. Reason, grounding, capability, policy, operations, persistence, observability. Now we add the complete running and demo execution section, so the Capstone can be narrated exactly as a live system walkthrough. From the project root, dependencies are installed from requirements.txt. Variables are loaded, including OpenAI underscore API underscore key, model, embedding underscore model, and remote underscore MCP underscore URL. Then the Chapter 6 app is started with Python app.py. The interface opens at http://127.0.0.1:5050. At this point, the runtime console is live and connected to the full orchestration path. Now we perform the one-click demo walkthrough, one scenario at a time, with expected interpretation. Scenario 1 is activation failure. This scenario represents a frustrated support user with a payment to activation mismatch. The key system question is whether this can be handled autonomously or needs escalation. In this case, the system typically retrieves support context, scores lead as low, and may escalate if risk or friction language triggers policy. What matters in narration is not only the final answer text. What matters is that the response includes clear next action and that guardrails are checked before autonomy is allowed. Scenario 2 is refund complaint. This scenario tests emotionally charged complaint handling. The key behavior to explain is risk-aware tone and escalation readiness. Even when the request is operationally common, aggressive language and dissatisfaction may require careful handling. The system should produce a controlled customer reply, then either keep autonomous handling with low-risk posture or escalate if policy threshold is crossed. This scenario demonstrates behavior control under customer frustration. Scenario 3 is enterprise lead. This scenario tests business signal extraction inside a support-style conversation. The message includes team size and integration intent. The system should reflect higher lead_score and provide a follow-up-oriented response. This is where students see that the same agent can do service plus opportunity routing. The important explanation is that lead scoring is not random text decoration. It is structured output used for prioritization and potential handoff decisioning. Scenario 4 is duplicate case. This scenario intentionally repeats or closely mirrors a prior unresolved issue. The correct system behavior is duplicate detection against open tickets. Instead of creating fragmented parallel cases, the workflow should mark duplicate or link to existing unresolved case context. This protects operations from queue pollution and inconsistent resolutions. This scenario is critical to explain operational maturity because production reliability is not only about new case handling, it is also about preventing duplicate case chaos. Scenario 5 is legal and security escalation. This is the strongest policy stress test. The message contains explicit legal or security risk markers. The expected behavior is direct escalation to human queue with a clear escalation reason. The system must avoid overconfident autonomous closure. This scenario demonstrates that guardrails are active controls, not passive labels. Now we explain how to read the right-side operational evidence during every scenario. First is guardrail decision. Guardrail decision answers one binary question. Should this case escalate or not? It also gives reason and risk flags. If risk flags include legal_risk, security_risk, or sensitive_information, the narration should explicitly connect those flags to escalation outcome. This is policy explainability in action. Second is trace payload. Trace payload is the full diagnostic record for the request. It contains trace_ID, execution mode, tool payloads, and guardrail output. Proves how the result was produced. Asks why the model replied this way. Trace payload is the evidence. Narration should highlight that trustworthy AI systems expose this chain instead of hiding it. Third is case table. Table is the live operational board. It shows ticket_ID, status, and lead score for recent cases. This table confirms whether escalation created actionable case artifacts. It also reveals lifecycle progression such as assigned underscore to underscore human, human underscore action underscore taken, customer underscore notified, case underscore closed, or duplicate. The narration should emphasize that this is the bridge from AI decision to real support operations. Now we close the demo section with one integrated interpretation. Across 5 scenarios, the same architecture demonstrates autonomous support, escalation discipline, lead-aware handling, duplicate protection, and persistent case operations. That is the core signature of production-grade agentic AI. Now, the most important teaching conclusion. A production AI system is not one prompt and one reply. It is a coordinated architecture where each module owns a clear responsibility. RAG owns grounding. Tools own domain actions. Guardrails own risk boundaries. Orchestrator owns workflow sequencing. Ticketing owns human continuity. Schema owns structured contracts. Trace owns explainability. When these components are designed and connected correctly, the system can scale from demo behavior to enterprise behavior. It can answer when safe, it can escalate when necessary, it can persist accountability. That is what real agent engineering looks like. Now let us close with what we have actually implemented. We built a real agent workflow that can understand user intent, retrieve grounded context, call capabilities through MCP, apply policy guardrails, and convert escalation decisions into persistent ticket operations. This is not a toy chatbot. This is an operational AI pattern that can run inside real support teams where accuracy, safety, and accountability matter every day. In real-time business use, this agent can reduce first response time, improve consistency of customer handling, prevent missed high-risk cases, and create clean handoff continuity between AI and human teams. It can triage faster, route smarter, and preserve complete trace evidence for audits and quality review. That combination creates measurable impact in service quality and operational efficiency. Using the same architecture, students can build domain-specific agents for many business needs. For healthcare operations, the same flow can triage patient support requests with compliance escalation. For banking or fintech, it can handle account issues with fraud and legal guardrails. For e-commerce, it can manage refunds, delivery disputes, and VIP customer routing. For HR, it can support policy questions, onboarding workflows, and sensitive case escalation. For internal IT, it can automate incident intake, severity classification, and human handoff tracking. Thank you everyone for joining this Capstone journey. You did not just learn prompts, you learned how to build a complete, reliable, and production-ready agentic AI system. Keep practicing, keep building, and keep experimenting with real workflows. We will hopefully meet again in the next course. Till then, enjoy agentic AI.